Hope you're having a great day. Today we are going to look at the concept of molarity. Okay. And so our goal for today is that we will be able to describe the concentration of a solution in terms of molarity. So let's unpack that goal a little bit. So when we think of that word concentration, we're going to want to think about how much of one thing is in a certain area. Okay. So when you guys think of something that's very concentrated, there are a lot of particles or there's a lot of objects in a specific area. If something is not very concentrated, things are very spread out. Okay, so when we talk about concentration, that's going to define the amount of particles in a certain area. So again, when we think of something being concentrated, we have a lot of objects or a lot of things in the area, whereas something is not concentrated, it's going to be more spread out. Okay, so we're going to be looking at how many particles we have in a specific area using this term molarity. Okay, how spread out are our particles, or how many do we have in a given space? Okay, so before we look at this, we're going to do a little vocab review because these are going to come into play. The first one from our previous unit is going to be solute. Remember, a solute, that's a substance being dissolved. So if we look at Kool-Aid, the powder, okay, that's solid, that would be our solute because we're dissolving that powder in water. That would then make water our solvent or our dissolving medium. Okay, that is the one doing the dissolving. And when we have a solute and a solvent, that is going to make a solution. Okay, so a solution, that's going to be a homogeneous mixture where one substance, that's solute, is evenly distributed throughout another, which is our solvent. Okay, so what we're going to do today is we're going to be we're going to be looking at how much solute we have in a specific solution to describe its concentration. An example, let's look at a solution of Kool-Aid. So again, for Kool-Aid, our solute, that would be the powder, and our solvent, that's doing the dissolving, that would be our water. Okay, so in this Kool-Aid, we can describe the concentration of that Kool-Aid. If we know from prior experience, the darker the color red of that Kool-Aid, the more concentrated it is. Okay, the more intense that flavor is. And if we want it to be a darker red or more concentrated, well, one thing we can do is Kool-Aid powder we have in that drink mix. Okay, so the more solute or the more Kool-Aid powder we add to that drink mix, the higher the molarity would be. Okay. Another thing that we could change would be to lower our volume. So we can see if we have more powder in a smaller amount of volume, it's also going to make our concentration greater, okay? Because in that certain area, we have more particles. On the flip side, if we decrease the amount of Kool-Aid powder in our solution, we can see it turns a lighter red, okay? It becomes less concentrated. We have less particles in that certain area. Another way we can decrease that concentration, if you think your Kool-Aid is too strong a flavor, is we could add more water. So when we increase the amount of solution we have in total or the amount of water we have, that would also decrease our concentration, okay? Because now our particles are more spread out and they're not going to be as tightly concentrated in just one area, okay? So if we look, we're going to see this word molarity up in the upper right-hand corner here, and that is going to describe how concentrated our solution is. And that's going to depend on two things: the amount of solute we have, so how much Kool-Aid powder we add, and the volume of our solution, because we see changing both of those values impacts that concentration. The more solute we have, the higher the concentration, whereas the greater the volume, the lower that concentration. To increase our concentration, we wanted to add more solute particles. Okay, the more solute particles we have, the more concentrated that solution is going to be, the more particles we have in a given area. Something else we could do is decrease our volume of the solution while maintaining the same amount of particles. Because if we have the same amount of particles, but decrease the volume, those particles are going to become more tightly packed. And our solutions can become more concentrated. On the flip side, if we wanted to decrease concentration, we would have less solute particles so that those particles can become more spread out. Okay? And if we kept the same amount of solute particles, we could increase the volume of solution because then the particles that were already there can spread out even more, causing that decrease in concentration. Okay. The main unit we are going to use in this unit to describe concentration is going to be molarity. Okay. So molarity is going to be one way to represent the concentration of a solution. Okay. And the units for molarity is going to be capital M, which represents molar. Okay. And that is going to describe how concentrated our solution is. The greater the molarity, the greater the concentration. So when molarity, we need to take these two things into account. Our molarity is going to be equal to the moles of solute we have, so the moles of substance we have dissolved, divided by the total liters of our solution. So that equation for molarity takes into account the moles of, or the amount of solute that we have, and how large or how large our volume of the solution. How many liters of solution do we have? Let's say we wanted to make a 1.2 liter solution of 1.5 molar NaCl. So now when we see that giant M, that tells us that 1.5, that is the molarity or the concentration of our solution. Okay. And remember, molarity is equal to moles over liters. So moles of solute divided by liters of solution. So if we want to find how we would make a 1.2 liter solution of 1.5 molar NaCl, we need to figure out how much sodium chloride we would need to add to this 1.2 liters of solution. So what we'll do is we'll plug our values into our equation. So we'll set our 1.5 molar equal to moles of solute, the moles of our NaCl, over our volume of 1.2 liters. We'll multiply each side by 1.2 to get moles by itself. And when we do that, we'll find that we would need to add 1.8 moles of NaCl. So something to keep in mind here is when we are actually in a lab, unfortunately, we can't measure out moles. So what that means is we are going to need to convert this 1.8 moles to grams. Okay, because if we want to see how we would actually make this, we're going to figure out how many grams of sodium chloride we would need in the solution. Okay, so if we look at NaCl, to convert to grams, we use that molar mass. Remember, to get our molar mass, we look at the periodic table. Sodium is going to have a mass of 23. Chlorine has a mass of 35.45. That means our total molar mass here would be 58.45 grams per mole. Okay. So we'd multiply the top by 58.45 grams. So we would find if we wanted to add 1.8 moles of NaCl, we would need to add 105.21 grams of NaCl. Okay. So to make the solution, we would need to add 105.21 grams of sodium chloride to get our 1.8 moles. And then add water until our total volume is 1.2 liters. Okay. So in this problem, we were able to use our molarity equation to figure out how many moles of NaCl we needed. But then if we're actually in the lab, we would need to convert those moles into grams so that we can actually mass it out. Problems will be pretty nice because we're always using the same equation over and over. It's just we'll know different values. Okay. So likewise, if we look down at this bottom one, we want to find what value of KMnO4 could be produced if we have 45.25 grams of solid KMnO4 added to water. So again, you see this giant M. That tells us this is our molarity. And we know molarity is equal to moles of solute, which in this case is our KMnO4, since that's what's being dissolved, divided by liters of solution. Okay. So if we look at our problem, we know our molarity is 0.3. We do not know our liters of solution. That's what we're trying to find. And unfortunately, our problem doesn't come right out and tell us moles. But what it does tell us is that is our mass in grams. So we know we have 45.25 grams of KMnO4. So in order to plug that into our molarity equation and solve for volume, we're going to need to convert those grams into moles. Okay? So for every 1 mole of KMnO4, we'll look at our periodic table to find that molar mass. And we know that potassium has a mass of 39.1. Manganese, or Mn, is going to have a mass of 54.94. And then plus oxygen, which is 16, but we have 4 of them. So we'll have to add those all up. So when we add those together, we'll find that our total molar mass ends up being 158.04 grams. So if we have 45.25 grams, that ends up being only 0.286 moles. Okay. So now that we know our number of moles, we can plug that in to our molarity equation. Okay. This one's a little bit trickier to solve for because that liters is in the denominator. So if that's the case, get liters out of the denominator first by multiplying each side by that volume. So then we'd have our 0.3 molar times our volume measured in liters is equal to 0.286. And then we can see to get the liters by itself, we would need to divide each side by 0.3. And we would find here that we would end up with 0.954 liters as our volume. Okay. Something that might be helpful here as you're solving the problems is we'll also need to know that there's 1,000 milliliters in 1 liter. So be wary as to whether or not they give you your volume in milliliters or liters. So just make sure you guys are paying attention to that. Okay. All right, but main idea here is use that molarity equation to describe how concentrated your solution is, and we'll just solve for different parts of it. Just make sure we always do moles of whatever is being dissolved divided by the total volume of solution in liters. Okay, that'll tell us how tightly packed our particles are. All right, I hope you guys have a great day. Please let me know if you guys have any questions.